So today is one of those rare days where I'm not going to do an activity out of the textbook. Instead, it's going to be more like a traditional lecture, as again, I feel like it's important to go over for loops as many times as I can and as much detail as I can, because this is where basically we concentrate most of our efforts. So last time we were concentrating on for loops with regards to using it to draw a circle or just to draw in general. And today we're going to just keep it more abstract, although we still are going to deal with stuff about pi. Last time we had to mention pi. This time we're going to eventually work up to calculate or working on an approximation of pi. But for today, what we're going to do again is focus primarily on the for loop. Going to review and go into more depth about what we did yesterday with regards to how the for loop is used for repetition, and then we're going to move on to how we can about the different kind of ways we can use a for loop and what more the grammar is. Okay, if you weren't here yesterday on Tuesday, or missed it yesterday, or have forgotten because that was a long time ago, let's go ahead and I'll talk about what the for loop is. So I'm going to go ahead and save this. So I've opened up idle. I'm going to go ahead and save this to my desktop. For loop overview. Assuming it can spell loop. Apparently I really wanted to spell it lop. So let's see. So a for loop looks like this. It's going to be for x in y, where we're going to replace x and we replace the x and y. Notice that the for and the in are keywords. They lit up a bit differently. They're built into Python, and you can't really use them for anything else. You can't use them as variable names or anything. They're special words that are off limits, like if and while and def and let's see, is it assure? No, that's a different one. As, though, and lambda, I'm pretty sure. Yeah. There's a few special built-in ones. There's a list that's in your textbook and on the Python website. You'll know because it will we'll get into this orangish color in idle or some other color. But these just kind of highlight to let you know the word has special meaning. Now the word over here. Now the way you read these for statements are for each x in y. So for every x in y, for each x in y. If you did learn quite a bit of Java, then for instance, so this is just for people who know Java or did quite a bit of Java. This is equivalent to the Java's for each loop, which looks something like this: for object O in, and they use a colon in Java rather than an array, in whatever your collection was. And yes, you may not have seen that in Java, but if you haven't seen it, if you took Java in high school or somewhere else and you've never seen this loop before with a colon in it as opposed to semicolons, yeah, there's a second for loop in Java. It's the for each loop, which is the one Python's going to use. C doesn't do this. Same with C++. It's the for each loop. So it's read for each x and y. Yesterday we learned to just kind of ignore. Tuesday we just kind of learned to ignore this, and we learned about about this special word called range. So for blank in range 5, print hello. Basic over here, save it, run it. Hello, 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 right? So whatever is inside of this for loop is going to occur this amount of times. If I change this range to 3, it's going to occur 3 times. If I change it to 100, it's going to take 100 times. Now, mind you, my computer is not slow, neither is yours, but printing out 100 lines of something will take time. So, if you do end up putting in a really large number, you may have to go over here and hit shell, interrupt execution, or just hit Control C, which will crash the darn thing. Ideally, may be hard to interrupt it. Or you may have to hit the X button, which will say kill, in which case that's okay. You know, so just be aware that putting in a very large number there, you know, if you do that, don't wait for it to finish if you realize that this is going to take forever. Go ahead and prematurely just stop it. So there we go. This occurred, you know, this prints out 10 times. Let's go ahead and let me go ahead and change this back to a more reasonable, easy to see, easy to visually count thing. Hello, 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 range 3, and print world. All right, just so remember, the other way that for loops work, as I mentioned, is that for loops will repeat something. What does it repeat? It repeats what's inside of it. How do you know what's inside of it? It's been indented inside of this. So for in range 3, we're going to print hello world, hello world, hello world. Right? Makes sense so far? Hello world, hello world, hello world. Because these two statements are inside of this. If world was on the outside, it goes hello, 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 world. And just so that it doesn't look, so that you don't get scared later on, print done. So here we have two statements inside, one on the outside. Hello, 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 world, world, world. Sorry, we're not hello, hello, hello. Hello, world, hello, world, hello, world, and then done. Right? Hello, world, hello, world. So it repeats what's inside of it, then starts over. Repeats what's inside of it, then starts over. Does what's inside of it, then starts over for a total of 3 times. And then after it says, oh, there's no more repeats to do, it moves on over here to done. If done was indented, there you go. By the way, don't panic just because I do this. This is a preview of very much in the future. There's nothing stopping you from nesting these things. Let's go with 2. You can nest these as deep as you want, although if you go more than 2 in Python, something's wrong with you. Don't do that. Occasionally, we will do nested, you will have to deal with nested loops, but definitely not today. Just know that, like, the language gives you the freedom to do what you want with it, including nesting these things as deep as you want. But of course, you know, here be dragons at the moment. So we're not going to deal with that. Just hello world. Hello world. So this kind of repetition thing is very useful for when you want to do something a known amount of times, or you want to copy and you don't want to copy paste, or when you want the user to tell you how many times you want to do something. So for instance, with that, say that you want to say, so say over here, input, just very quickly, input, num times equals int. So we're going to get a string from the user. It's going to be how many times to say hello? Question mark. I don't know why that happened there. 1 second. How many times to say hello? That's why that happened. Right? And then we'll turn that into an integer so I can actually use it. Int. And I'm just going to do this on purpose right now. Run it. And I want it to go say hello 100 times. And it does it, looks like once. int num times. So let's go ahead and see what's going on. Did something go wrong there because it should have said it only 3 times. 10. There you go. And it says it 3 times. It does hello world 3 times. Why? Because while I did read a variable from the user, I didn't do anything with it. Very common mistake there. That doesn't matter how many years of programming you're going to have. You will constantly make this mistake where you'll create a variable, and then you're like, oh, right, I totally forgot to use it. So here, we get a user. We ask them how many times they want to say hello, and we'll put this in. And now it's going to vary based on how I run this. So if I say I want it 5 times, I'll do 5. If I want to say 10, it'll say 10. And if I say it wants apple number of times, it's going to tell me apple's invalid for converting it into an integer, I would hope. So, okay. So that's one. So that's a good use case of. So being able to repeat something a set number of times is one of the big uses of being able to use a for loop. Okay. And that's going to be very helpful in Lab 3, for instance, with the turtle clock assignment, which basically wants you to draw this kind of clock shape, where basically you've got, okay. No, I don't want a daily stand-up project planning. I want just a blank canvas. Why is that so hard, Microsoft? Okay. So the turtle wants you to you'll draw a clock and it kind of looks like this, where you got this, and then there's the turtle, and then there's the turtle, and there's until we 6, 7, 8, 9. There's the turtle. 10, 11. It doesn't matter. So anyway, what we're going to do is that we would draw this clock, and there's going to be 12 total strokes to it, right? So like here's 6, 7. Well, 3 o'clock would technically be over here. 3, 4, 5, 6. Okay, yeah. Apparently, I don't know how clocks work. Okay. So we'd be drawing this. There's there's a line. There's a gap. There's a turtle. It's the same thing we're going to be drawing every single time. Okay. So rather than drawing it once, drawing it like the entire thing, draw it once, then have it rotate, and keep doing it. It's the and then you do that a total of 12 times. It's not so that for loop saves you that work of having to do it. You can do it without the for loop. It's just going to take you 12 times as long, or have to copy and paste, and then you're going to have to check how many times you actually copied and pasted to make sure you didn't do it too many times. So these for loops can be very useful in saving you some effort there. But the primary use is to iterate over things. It's an iterative statement. We technically we have 2 types of loops in any programming language. Okay. Right now, what we're learning is something called the determinate. Is it it? I can't. Determinate loop. Okay. It runs a deterministic amount of times. Determinate loop. It runs some set number of times. So with the for loop, we say you want it to run 5 times, you want it to run 10 times, or say you want it to run, so 5 times, 10 times, or say, oops, there, forgetting the colon there. Or you want to run, as any sane person might, an apple number of times. We'll get into that in just a second. But the behavior there, when I put in apple, was not random. It ran 5 times, once for each letter. It runs a determinate number of times. So that is your for loop in every language. Indeterminate. The indeterminate loop is your while loop, where you aren't sure how long it's going to run for. This is a good thing if basically you're asking the user to input something, and then you're checking their input to make sure it's valid, because users can be very bad at putting in valid data. So that's what the while loop is often for, or if you need a loop that runs forever, or you just don't know when you're going to trigger your condition with a while loop. So right now we're dealing with things with loops where we know how long something is going to last for. Okay. If I wanted to know how to spell correctly, I would have gone for an English PhD. Didn't go for one of those. So, all right. So let's go ahead and take a look at what else we can do with this. So with this, what we're going to do is we're going to look more in detail about what we can do with range and how that works. So now rather than doing, yes? It's a comment. What it does is that it says to the computer, do not read this. This is human. This is for humans' eyes only. So you can typically use comments for like this. For non-code things as well. You can also use comments to just turn off a line of code. Yes?
But it was still reading the code and it printed.
It didn't, but it doesn't run what I have commented out. I commented this part out just to simply turn off these codes and leave them kind of in notes. So let me type this out. So let's go with X in range, or actually let's go with num. We've got, let's make it a bit less abstract, because again, we can use multiple letters for a variable, so we should, as opposed to like overloading every letter to the point that we have to go into the Greek alphabet and start having to use those like they do in math. So for num in range 5, okay, print hello. Right, just like in like I was doing earlier with num times, if I create a variable and I don't use it, then it's just not going to get used. So here I'm saying, and let's go back to what I said at the beginning, you read this for every x in y. So for every number in range 5, print hello. So what does that mean? Well, let's go ahead and print out that number. Okay, for every number in range 5. Range 5 is apparently 0, 1, 2, 3, 4, and then we print out done. Now, if you look at that, that's a total of 5 numbers, 0, 1, 2, 3, 4. In computer science, in almost every language, we start our counting at 0. You'll see why very shortly, but the point is to make our math easier. It makes the math for figuring out how many times we do something, or how long something is, or how big something is, quite a bit easier. So we start at 0. So 0, 1, 2, 3, 4, that is 5 total numbers. Okay? If I did for every number in range 0 to 3 is what it's going to say. 0, 1, 2. For those of you who have taken the appropriate algebra classes or are taking those, the range function, when we look at it like this, oh, come on. I don't know why this turns off. You shouldn't turn off. You're a pen. Okay. It is the equivalent of us saying, okay, come on. So basically we put it, so range to some endpoint. Why am I typing it here if it's not working? Okay. Sorry. So if I've got comments, range to some endpoint, is equivalent to all the numbers, well, not all the numbers, but all ints from 0 to endpoint, and then that parentheses there is intentional. If you remember, that is the inclusive, including 0 up to, but not including the endpoint. So from 0 to 3, it's from, so for range 3, that is 0 up to, but not including 3. Okay? So 10. Okay. 20, again, it doesn't really matter what integer we put in there. Does it matter if we put in a float? Yes, it does. It in fact does matter. Only integers are valid in range. Make sense? Because we're looking at the integers between 0 to the endpoint. There are no, once we introduce floats, it gets a bit complicated. And so better to reject them entirely. Negative numbers just won't run because from 0 to that endpoint, there's no numbers in that endpoint, right? It kind of like, instead of being from this point to this point, it's kind of from this point to this point, and you can see that that doesn't work there. So that seems like a bit of a issue. It is, but we can work around it. Okay. Now, so this can be useful because this can vary. As I did at the end of the last lecture, I can do things like change the color over time with this, or increase the value over time. I can create spirals using this in Turtles. Mathematically, what I can do is I can create something called a running sum. I can create a variable over here. Let's go ahead and keep this down and nice and simple. Let's do 3. Total is equal to 3, not 3, 0. Total is equal to 0. For each number in range up from 0 up to, but not including 3, total is equal to the total plus the number. This is a very common thing we'll see a lot. Print total. Now, you'll find that I'm a very big fan of doing things the hard way first, and then showing you an easy way, as well as doing things easy first and then going really harder than it needs to be, so that when you go back and look at it at your homework, you're like, oh, this is much easier in comparison. So total is equal to 0. This sets a variable called total equal to 0. I don't use the word sum because that's already the name of a function, and I don't want to confuse things later, so I use the word total. So for every number, what I do is I take what's the value currently in total, add the number to it, and store it in total. So we do that for all the numbers from 0 up to, but not including 3. So we start at 0, and we add 0 to 0 to get 0, and we store it in total. Then number's value is equal to 1. Okay? Number's value is equal to 1. So what we do is we do 0 plus 1, which becomes, this entire thing now becomes 1, and we store that in total. Then we get to 2, we do 1, and then 2's value, this is 2, 1 plus 2 is 3. We learned that probably in kindergarten. So we store that in total, and then we print out our total value. So we can use this to do a running sum, right? We can, in fact, print this out as we go along by saying we got the total here, and then we can put an equal sign to kind of print out, to make it look like an equation. Is equal to, well, it doesn't necessarily work there. Total is equal to what we had before, total minus number, plus the total minus number will give me what I had before, plus number. right? It undoes the addition operation that I'm about to do. And now we started out at 0. This was our first step through the loop. Next number was equal to 1. Then, so we added 0 to 0. That's why 0 is over here. We add it to 1. Sorry, we add 1 there, and we get 1. Then we take our value for total, add 2 to it to get 3. Make sense? So let's go ahead and look at 10. Goes the same way. We start out at 0. Our total is equal to 0. We add 0 to 0. We get 0. We stored that in 0. Next thing, in fact, why don't we go ahead and rewrite this as a arrow, just to kind of make that. So we take 0, add 0 to it. We store that in total. We take our total, add 1 to it, and store that in total. We take our total, which is 1, add 2 to it, store that in total, which total is now 3. We take our total, which is 3, add 3 to it. So 3 plus 3 gives us 6. We store that in total. 10 gives, to get 10, we took our total, added 4th to it, right? 0, 1, 2, 3, 4. It's 4's turn to be added. So we get 10. Then we take what's in total, add 5 to get 15, so on and so forth until we get to 45. Make sense? We're just basically adding one number at a time here. Okay, the more we do it, the less foreign it will look. Okay. Let's go ahead and, again, I'm going to comment this out so that it just stays around. You can use, for a multi-line comment, you can use 3 quotation marks. Basically to say, hey, 3 quotation marks in a row, start a comment, end the comment. Make sense? So that way I don't have to put a tick mark in front of everything. Okay. Yes?
I'm not sure if you said it already, but when you do range 10, why doesn't it include 10 in the output?
It's just when I,
Yeah, like why doesn't it have a 10?
it's all the numbers from, so for range, it's all the numbers from 0 up to, but not including 10.
Okay.
So the range is the endpoint and it never includes the endpoint. I'm actually about to go into why that is.
Okay.
So it's a very good question. So let's go back to just simply looking at now the way the range function works. For num in range, okay, we've got ourselves a range. This is about all we need to know for today, but we might as well note that sometimes as you're typing in Python, as you're typing something that's built into Python in idle, it will come up with suggestions. It says range, stop, which is what we've been doing. It's what I've been calling our endpoint. It says, okay, so you can put in a stop. You can also do start, stop, and step. So let's go into that. Range 5 to 10. Print num. So we can give it a two numbers. And not scary at all, it does 5, 6, 7, 8, 9. So it allows us to define the start point and the end point. In fact, by default, what's going on when I do this, when I do let me go ahead and copy this. When I do this, by default, what's going on is it says, oh, range 5, you mean, it's just kind of going and filling in the blank for itself. Oh, you mean range from 0 up to 5, but not including it, right? So it's automatically kind of putting in a 0 in if you only give it 1. Make sense? So 0 to 5. So you can define the start point. And this prints out 5 numbers. Prints out 5, 6, 7, 8, 9. 10 to 20 will print out 10 numbers. And let's see. 111 and 12, that should print out 100 numbers. Sorry, 99 numbers total, which I can just tell without actually having to count it. Now, why can I do that? Even though it's a weird range of numbers, it's because what I'm going back to is that the reason we don't include the 0 is to make the math easy. To figure out how many times something is going to print in total in a range function, you can just simply take the endpoint and subtract the beginning point. So 10 minus 5 gives you 5. It's going to print out 5 times. This will print out 6 times, right? 5, 6, 7, 8, 9, 10. Make sense? So that's part of the reason why we start at 0, because it will make the end, we don't include the endpoint. It makes the math for figuring out how big these things are much easier. And remembering the 0, once you get used to it, is super easy. Remembering that it doesn't have an endpoint, that the endpoint isn't inclusive, also super easy, because pretty much everything, with one exception, does not include the endpoint. And let's see. So 5 to 10, we can do, again, whatever kind of range we want. 5 to 10, 50 to 100, that's going to print out all the numbers from 50 to 99, which is 50 separate numbers. And final, let's see. 100 to 50, of course, will print out, unfortunately, nothing still. So this is where the third argument comes in. So before we go too far off the deep end, though, let's go ahead and just see what we can do with that third number, because optionally we can put in a third number. By default, that number is 1. By default. Again, if you don't provide that third number, it's automatically going to provide it. It's 1. So what happens if I change that number to, say, 2? 50, 52, 54, 56, 58, 60, 62, 64, 66. Again, the least surprising kind of thing. By 5s, we'll start counting up by 5s. And then if I were to do it by 10s, and then if I were to do by negative 10s, it's not going to work, right? Because you can't count down from 50 to 100, right? On the other hand, what we can do is go from 100 to 50 by 10s. Now notice it prints out 10, 90, 100, 90, 80, 70, 60. Doesn't print out 50. Same rule applies. We're not including the endpoint. We never include the endpoint. If we change that rule, you'd have to remember we changed that rule. Just remember we never include the endpoint. Make sense? So there we go. We're not really going to have to use that much in this homework, the next homework. It's just but these can, actually lab 4, you might use this in one to make your job a bit easier for one of the problems, but it's not required for lab 4/5. Okay. Finally, let's go ahead and talk about one other thing I can do with this before we go on to our big topic for the day. I mentioned you can use it. It's for each x in y, and I kind of already showed you what that other y could be, or one of the other y's could be. Let's go ahead and make a variable. I'm going to call it let's call it word. I'm going to say tacos, tacos, tacos. Actually, let's just go with I love tacos. That way we've got just a full sentence. We've got a good range of things. We've got spaces. We've got we've got this. And one of the things you'll want to do with your font, by the way, if you're, what you want to make sure is you're typing, and this is kind of thing to do on your own time, is make sure that that when you're reading your code, the font you're using, you can easily tell the difference between an uppercase I and a lowercase L. Especially important if you're a non-native English speaker. Same for I's and J's. You want that to be pretty darn distinct. And finally, of course, you want your zeros, your O's, and your O's to be distinct. These are things that most fonts do, but if most monospace fonts will do that, and that's a font where basically every character is the same amount of space on the screen. See how everything takes off the same rectangle? Doesn't matter how you might actually draw it on paper. A lot of fonts like Times New Roman or the like, they are for reading and follow, a lot of old things about, printing presses and stuff with being able to, and you want as much space on that so you can make certain characters thinner. And that can make some characters hard to distinguish. So give yourself something that's easy to read. So here we've got I love tacos as my input string. Okay, and I'll just do this, and I'm going to use easy to use language for my variable names, so it's easy to see. 4-letter in Word. Print letter. Fairly straightforward. Now I could call this anything else. Technically, these things aren't letters, right? The spaces aren't letters, technically speaking. And same with the punctuation. I could call it glyph or something like that, or symbol, but honestly, letter just, it flows much easier in your narrative understanding. So what I do is I can go through each letter in this word, and I can print it out one at a time. I space, and printed out a space there, didn't just leave it blank. LOVE space TACOS period. Right, prints out all the characters. And it's going to print out how many ever characters there were in there, which were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total characters in there. So we can iterate over those kind of things. Okay. So again, these for loops can be very powerful. We're going to learn how to use these in more detail. But for right now, we're just trying to get you to understand the mechanics of this. This for loop is going to be very useful for kind of just doing things like being able to draw squares with turtles and triangles, and not have to, write the same code over and over and over again. So now let's go ahead and make a segue for a bit on the step away for about 10 minutes on this, and talk about pi. So specifically, I'm talking, of course, about the Greek symbol number pi. Again, I love Wikipedia. Actually, I don't know if I've mentioned that enough in this class. Wikipedia is fantastic for mathematical and computer science articles. For instance, this is a great representation of what pi is. Here we have a circle with a diameter 1, and we see that basically that if we unroll it, diameter 1 means a radius of 1/2, which means the diameter total is pi. We can see what that means. So if the diameter is 1, if we unroll the circle, it comes out all the way to around pi. It's a nice visual representation of it. All right. So pi is what we call an irrational number, which means that's a number that you can't accurately represent as a fraction. You can't represent it as something that is a fraction of two real numbers, which means, unfortunately, it will not terminate, meaning it goes on forever and ever and ever. However, that being said, you can use fractions, and people did use fractions to approximate pi. Depending on where you were in the world and what time of history, it would be a different number. 22/7 was a very popular way of approximating pi. If we pull up the calculator, okay, we pull up a calculator. Let's just go ahead and look at that. We didn't need to pull up a calculator. I could type it into Python. 22/7 gives us 3.14, so it gives us 3 accurate digits. It gives us the 3.14, which is what you learned in grade school for pi. 3 numbers. Everybody can basically remember 3 numbers. Okay. Now, these days we've gotten more and more better with our approximations. We can use fractions were used for, let's see, some Egyptologists say that they use 22/7. Babylonian mathematics usually approximated pi to 3, which, believe it or not, is sufficient for a lot of architectural projects back in the day. 25/8 gave 3.12, which is about 0.5% error. Let's see. So looks like the Indian peninsula or subcontinent did 339 divided by 108, which gives 3.139. Let's see. Chinese mathematician, this is a really good one, really good approximation over here, which is 355 over 113, which were not as good as their other results that they were able to do, but they were really good for what the kind of work you needed to do. Now, eventually it was kind of discovered that there were mathematical formulas you could use to approximate this value. You could create what's called an infinite series, and that would converge to pi. What that means is that basically you'd have some series of numbers, and the more operations you did, the closer and closer and closer the value would be to pi. So today what we're going to look is something called the Madhava-Leibniz series, also just simply a lot of times referred to as the Leibniz series. It was originally named after Gottfried Leibniz, a famous mathematician, but he discovered it in, so Madhava discovered it in the 14th to 15th century, whereas Leibniz and James Gregory both independently discovered it in the 1670s. It's one of those things about naming things in mathematics and computer science. We often find that what we found was discovered was also independently discovered by other people much earlier, and we just didn't know because it was written in a different language by different people. So let's see. This is so we don't need to look at all this scary math over here. What we do want to look at is that basically is this formula over here, which is, actually, I can just open it in a new tab, can't I? And zoom in on it, nice and big. So it's a formula, and it goes like this. Again, it's an infinite series, meaning we can make this as long as we want. 1 minus a third plus a fifth minus a seventh plus a ninth minus da-da-da-da. So in other words, it's saying if you continue this pattern to infinity, if you eventually get to infinity, which you can't do, you'll get to pi over 4. In realistic terms, this means the more numbers we add, the closer and subtract, the closer this is going to get to pi over 4. Okay? Okay? And for reference, let's go and say what is pi over 4. Pi over 4 is, let's say, 0.785, right? So if we do 1, so over here, I will clear this. Actually, let me go ahead and just do this Python. 1 minus a third plus 1/5, and I'm putting it in parentheses so that it actually, registers correctly. Come on. Okay, there we go. That gets us 0.86, which is not 0.78. But we find if we then do subtract, notice it's a bit more than 0.78. So we subtract 1 over 7, which now undershoots it. And then we add in a bit more, minus 0.7 plus 1 over 9. And notice it's getting that when we added a ninth, now it's getting even closer to that 0.78 that we were looking at. So basically, adding more results will get it closer and closer to the real value. It's a slow process. I guess it must have been a real pain in the Tookus to verify by hand because you didn't have a computer to do it. Fortunately, we do have a computer to do it, and we can calculate it. So however, 0.78, we don't know that off the top of our heads. So what we'll do is that we'll calculate this series. We'll get pi, which will get us pi over 4. But when we print out our answer, we'll multiply it by 4. So we can get pi, right? Because it's pi over 4. Multiply it by 4, that's going to give us pi. You need assurance that will work, right? Let's just go to the approximation section again. And it says, yes, in fact, you can totally do that, right? Pi is equal to 4 times that entire infinite series. So how does that infinite series work again, right? Still not working there. So again, it is, let's see, have you tried turning it on and off again? Nope. I don't know why it's just stopped working when I was in Japan for some reason. I don't know why. All right, so 1 minus 1 over 3 plus 1 over 5 minus 1/7 plus 1 over 9. So what is the next term in this? What's the next thing we need to add? Yes? Minus 1/11. Then the next thing? Plus 1/13. Why? Why do we know this?
The denominator increases by 2, and then the plus minus just 1.
Right. So in case you couldn't hear that, because because you're all the way over there, the denominator increases by 2 every term. In fact, this 1 is, we can just simply write that as 1 over 1, right? It increases by 2 every single term that we get. And then the plus minus sign just flips each time around. So our object for the rest of the, I guess, half an hour that I have you, is that we're going to write a for loop that does this. Now this seems like it's pretty hard, right? How did we get from just simply doing a running sum, which already seemed pretty hard, to this entire thing? Okay? To this kind of issue. Well, let's just go ahead and put this over here for reference. 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 over 7, just so that you have it easy here for an easy reference, right? And let's go ahead and rewrite this as 1 over 1, just to make it clear that this is part of that pattern too. Okay? So how can I go there? Well, we did learn how to add stuff up with this running sum. Total is equal to total plus number. We've done that already. And for those of you who, and there was one thing I forgot to mention there, right? So some of you, this still feels really icky to, right? Where basically you say total is equal to total plus that, right? That looks really weird still. The good news is that there's a shortcut. This can actually be shortened into one with a special operation in Python and in a lot of programming languages called plus equals, which says simply change what's in here, and you can read that as change what's in on the left by this amount. Increment total by this amount. It's the computer, when it sees this, just simply transforms it back into this. But for a human, that sometimes is a bit easier for you to read, and it's certainly simpler for you to type. Make sense? The same thing. Okay. So I'll be using the really weird looking way, just simply so it can emphasize it and give you more exposure to it, but it's just also something I should mention. So looking at that and going from that to here, that looks kind of that classic, skipping from point A to point Z, But part of computer science is being able to look at a problem and say, okay, it's a big problem, but it's actually made up of these small problems. Okay? Problem 1 is adding arbitrary number of numbers. We know how to do that, a running sum, right? We're done. We know how to do that. Done. We use the running sum format. The total is equal to 0, and then we just simply add numbers to that total as we go up, right? In this case, we'll be subtracting as well. So that's on second problem. Problem number 2. Alternating between addition and subtraction, right? That's another problem. 3, let's see, adding fractions instead of number. So adding, or another way to rewrite that is another way we can rewrite that is adding, going from 1 plus 3 plus 5 plus 7 to 1/3 plus 1/3. Notice that I'm doing plus. I'm not worrying about the alternating. The alternating is a separate problem, right? 1 plus 1/3 plus 1/5 plus 1/7. Everybody get how that's a separate problem? Switching from alternate. So don't want to focus on both at once. And let's just go ahead and say problem number 4 is, so adding fractions instead of numbers. Incrementing by 2. So in other words, let's go into more detail in our comments. This is why we have comments, by the way, to kind of write down our thoughts before we start writing a program. I have a friend who works at Google, one of my best friends, makes close to $500,000 now per year when all benefits are said and done. And one of the things that got him through his PhD that is just an underappreciated thing that I want to bring this up because he did it and it's what makes him successful, is that there's a rush for a lot of programmers to start programming and start typing things out as opposed to doing this right over here. He prefers to do it with paper and pencil. I like to type it right in my comments over here. But the idea here is working out the problem rather than charging straight ahead into it. If you charge straight ahead into it, you might overcomplicate things or create just a tangled mass of spaghetti in your code. It gets really complicated to unwind then. So incrementing by 2. 1. So in that case, we want to go from 1 plus 2 plus 3 plus 4 plus 5 to 1 to 1 plus 3 plus 5 plus 7. These are all independent problems that can be solved one at a time in any order. What we're going to do is we're going to solve, first off, we're going to set up number 1. Add an arbitrary number of numbers. Okay? So we use a for loop for that, and we use what you're going to come to learn is a pattern for solving things. Total is equal to 0 for some x in y, which we'll replace in a bit. Total is equal to total plus x, print x. Now let's go ahead and fix that x so that it's a bit less mysterious or something. So first off, this is an infinite series. We want to add some number of numbers to it, right? So I'm going to just call that num terms, the number of terms we want to have in the series. I'll go with 10 to begin with. Okay, it doesn't matter. We can change that later. And so we want to add 10 total numbers. So I'll put range num terms here. This is the amount of times I want the loop to repeat, the number of terms I want to add. Make sense? So we're working on part 1 right now. And then we'll just simply add this number. And we get, let's see, total number of terms, 10, total is equal to total plus x. Why does it say 9? We're printing x. We want to print total. We want to print our answer, right? So we print out our answer for x in range num terms. We keep adding numbers to that. We print out our final answer. So which one do we want to work on first? We can work on alternating between addition and subtraction. We can work on working with fractions, or we can work on incrementing by 2. I recommend doing 4 before 3, but we can do either 2 or 4 first. Yes, 2? All right. So this one, it requires a bit of a logic leap, but once you see it, it's kind of hard to unsee it. Okay? Remember, tons of our operations in mathematics can be redefined as addition. Subtraction doesn't exist. You're just adding a negative number. That's another way to look at it. Same with multiplication. You're not actually multiplying. You're just adding a repeated number of times. So, but as far as adding a negative number, we can redefine this as adding -1 over here. We can have we're adding a negative value over there, a positive value over here, positive value over here, and we're adding a negative value over here. Make sense? Positive, negative, positive, negative, positive, negative. So what I'll do over here is I'm going to create a new variable. Or I'll create a new variable over here called sign to represent the sign. Okay? And I'll just set it equal to 1. Right? It's going to be either 1 or -1. So what I'll do is each time through the loop, what I'll do is I'll say, hey, I'll start with sign. So I'll take total, and instead of adding x to it, I'm going to do sign times x. Now, right now, this is going to do nothing in addition, because all I'm doing is just multiplying everything by +1. Now we wanted to get it changing between +1 and -1, right? Well, fortunately, -1's actually a useful tool there. Yes?
Could you put total equals plus equals sign times x?
Yep, I could. I could totally do that. I could do this. There's nothing stopping me from doing that. I just try to keep that a bit like that. We're not going to really mess with this part too much. Everything that's going to happen is going to happen over here. Sign times x, right? So what we're going to do is we are going to do sign times x. And so how do we change from positive to negative? How do we change a number from positive to negative? Sorry? Yeah, times it by -1. Right. We multiply that value by -1. That's exactly what we're doing over here. How we change this 1/3 to a -1, we multiply it by a negative number. Okay. So what we're going to do over here is a similar operation, except it's going to be multiplication. Sign is equal to sign times -1. So we add a positive number. Next time and then we say next time it's going to be a negative number. The time after that, positive. Because remember, -1 times -1, positive number. So we get -5 for this value. Why? Let's go ahead and print out our progress over here. Okay. Print total. We're going to print out our sign times x. Big X. Normally I won't do a big X like that. It's just bad practice. So 0, -1, 2 gives us +1, minus 3 gives us +1, 4 gives us +1. So it's just going to keep adding. It's just going to keep adding these numbers together, and the negatives. So you've got this value, which is one more. You've got this pair, which is, let's see. Actually, it's more like you've got this pair, which is -1. This pair, this is -1. This pair, that's -1. This pair, that's -1, and that pair makes -1. You've got 5 pairs that make -1, so you get -5. It's much easier than actually doing the math. So there we go. So we are done with this one. This one isn't so bad, increasing this amount by 2. Okay. We can change this from being the number of terms that might be limiting us. Instead, we could go from 0 to, but what we can do over here is we could go up by 2's, right? But if we go up by 2's, what values are we going to get? We're going to get 0, 2, 4, 6, 8, 4. Sorry, 0, 2, 4, 6, 8. Whereas we want 1, 3, 5, 7, right? So what should we change here to make it 1, 3, 5, 7? Yes? Change the 0 to 1. Why? Because our starting point is 0. Adding 2 to 0 brings us to 2, so we'll never get to 1. However, if we start at 1, our values are 1, 3, 5, 7, 9. This gives us 5 values. We wanted 10. So I can multiply num terms by 2 again. And now, there we go. We've got 10 values again. I just want the num terms to actually mean the number of terms I plan on getting. Okay, so there we go. And now the next step is we need to do fractions. Okay. Now one of the things you got to learn is that sometimes you got to change what you've already built, sometimes significantly. Okay. So really what we're changing, now what is changing in here? The numerator stays the same each time. It's always 1. So what's changing, what's varying, what we're doing over here, what this is indicating should be changing is the denominator. So let's go ahead and actually change that name, denom. I'm going to call it denom instead of denominator, right? Just denom. So rather than multiplying it by sine, I'm going to do, or sine times x, I'm going to do sine times 1 over the denominator, because that's where you put the denominator. See, this is where giving things names can be useful. Everybody understand why I went that way? Denom. So now what we have is we've got 1 minus a third. Well, that actually is going to give us a bit of an issue. So we will print out, so let's actually print out what we want to say, which is the sine time, and then we'll print out the times, because a lot of this is just simply for, the computer doesn't need this. This is for our sakes. Print out times 1 over, and then we want actually the, and then print, instead of printing this out, I'm going way too far on that, denom. So there, 1 times 1 over 1, 1 times 1 over 3, 1 over 5, 1 over 7, 1 over 19. And this gets us to 0.67, or 0.76, which, if you're like me, you may have forgotten it. I actually didn't forget it, but you know, I have in previous lectures. I've just done this lecture enough times that I remember that's 0.78. 0.76 is not 78, but you're not, you know, you have pi memorized. It's 3.141 something, 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 something. 3.14159, right? There's, instead what we can do here is that we will multiply that by 4. So we can switch from talking about pi over 4 to pi, and talk about pi over, and just talk about pi over 1. So this gets us 3.04, not 3.14. Although, interesting, it's 3.041, so that next digit is correct, oddly enough. So now comes the part which we increase the number of runs. You get to, with 100 terms, this gets us to 3.13. It's not 3.14 quite yet. I'm going to comment out this print statement because that's going to actually add significant amount of time to how long this takes to run. Okay? Increase it to 1,000. Do this 1,000 times, and you get 3.1405. 10,000 will give us 3.141. And then again, amazingly, just because of the way this works, 3.141 incorrect, correct term, 3.1415926. It's very interesting how it kind of is correct except for that one term. So now, 3.1415 And I'm serious about that, by the way. We can print out, let's go ahead and I'm going to go all the way up here. Import, math. Yes, that's something you can import. It has the things like sine, cosine, those kind of operations. And it has print, I believe it's math dot, I think it's math.py. Yep. So we can see that where it's so 3.1415, and then ours says 8.26535897.1. So it's correct for these digits, but this one is incorrect. It's the quirk of how this algorithm approaches things. And then once you fix that digit, the next one's going to be incorrect. So now we're working with about 1 million terms. Once it goes up to 10 million, my computer at least starts to chug a little bit, starts to really grind. And in fact, increasing it by another factor of 10 will make this take 10 times as long as the previous time. It's not even done, and I'm still talking, and I don't shut up, do I? But yeah, it takes a while. It took a while to get here. Again, this is not the most useful approximation of pi, but what it is useful for is showing us that we can break this kind of term down into this. We'll be approximating pi later in the semester using something called a Monte Carlo approximation, which sounds really scary, but that's actually just it's actually named after after a statistical technique that you use for gambling, among other things, and it's moved from gambling to serious scientific research. Seriously, a lot of the history of statistics and probability, that study, comes from gambling and mathematicians having to make a living giving advice to people who want to do better at their gambling. It's a wild ride. So there we go. And now, as far as this goes, let's see. So probably you've been frantically trying to type this down, and for some of you, it may or may not be working. So I'm going to share this on Discord. I'm going to pause that while this is going. So that's been dropped on Discord. You can find it on Discord. You can go and find, again, the link to Discord is on the Canvas page. I've dropped it there. I find that's easier to communicate that quickly because you can also download the code. You don't have to sift through your email. Also, if you really need to, you can go through the class, because this takes so long to do. And the other thing about email is that sometimes when I try to throw a Python script at you via email or announcement, it gets flagged because it's a Python script, which means it's a computer program, and sometimes security really doesn't like you sending the most innocuous of computer programs across the internet that can be run on somebody else's computer. So there you go. Anyway, Discord link is over here. Currently should still be set up for an infinite number of invites for an infinite number of time. If it gets abused, I just simply turn it off. It's not a hard thing to do. So regardless, that is essentially what so that's what I've got planned for the day. Now, one thing before I let you go, one thing that I want to show you, because this entire thing may have been like, oh my God, how do I keep track of everything through these for loops and how everything works, right? And this whole iteration process. There's a problem. Normally I would spend all this time going over, walking through an iteration. That's actually a classic thing you do when you're teaching this. But I don't need to. Because your book is awesome. It will, your code blocks can run through code step by step. Let me go ahead and open this up. I'm just doing this in the Scratch block over here. Total is equal to 0. For I in range, by the way, the classic value over here is typically I. We use I for two reasons. It's first letter in integer, first level in index. You'll see me use num a lot and index a lot when I mean those values. So let's go ahead and actually switch that. For a number in range 10, total is equal to total plus num. Print total. But how do I, and it will print out 45 if I run this. But how do I get there? Well, we have a couple buttons here. Save and run, which you're familiar with at this point. Download. Share code, which is on my end. But then there's this other button, which you may or may not have pressed. And sometimes you might want to try pressing buttons. Show code blends. And this is where one part of my job has become a lot easier. You can use this. So here, the red is the next line that's about to execute. The green is what just executed. So there, we've just created a variable called total. Inside of it is a 0. We've created a variable called number. Inside of it is a 0. Now we're about to execute this one. 0 plus 0 is equal to 0. We go back up. We went back up. Now num is equal to 1. So now we do we execute line 3. We go back to line 2. Line 2 says, okay, we need to increment to the next number. Add that in. And as you can see, you can step through this code until we get to that last line. It's a very useful tool. I do plan on going and stepping through things if needed. Now, the last thing before I let you go is anybody having any difficulty on any of the textbook exercises? Is there anyone that's like nonsensically difficult? No? Okay. In class, if if you find one over the weekend you find an exercise and it's absurd, and you're like, I've spent more than 15 minutes on it, and if you spend more than 15 minutes on a textbook exercise, what you should do is stop that and ask for help, or ask me at like the beginning of the next class, because I don't want you to waste too much time on those. All right? So you are free to go for the day. I'm going to go ahead and stop the recording and immediately upload it, but otherwise I'm available for questions.